Yeah, we are in the middle of a chapter. We started the part on equality constraint optimization, which is a bit improvised, and I promised to finish the script. I didn't finish it yet, but after this lecture I will sit in this room or in this building until at least a preliminary version can be uploaded. What I want to repeat is which setting we are looking at. We are in chapter 11, the one that we'll find. And we are looking at one specific optimization problem, namely one with equality constraints. And we already specified that this function g is a function from Rn to Rm. That means there must be m constraints that should be satisfied. And we are in the process of deriving optimality conditions. So what does a minimizer need to satisfy for this problem? And we already established a very simple theorem which says that when we look at all directions which are in the tangent cone of the feasible set, you remember there was important definitions, the feasible set omega and the tangent cone at some point in the feasible set was the direction that was a set of all feasible directions in which you could go, basically derivatives of feasible curves. Yeah? And this tangent cone plays an important role here. We so far only derived it in an abstract form. But what we already established and which we could easily prove is that if x star is a local minimizer of this problem, then this implies that first of all x star must be a feasible point, so that's trivial, right? But it must be. And the other thing is that for all p in the tangent cone at this point, it must hold that the objective cannot be improved by going in this direction. That means that the gradient of f at x star times any of these directions must point upwards. That's quite logical, and we established that already. The problem was that we cannot really have a grip on this tangent cone very easily, and this is what I want to do now, and which is much easier for equality constraints than for inequality. That's why we do this chapter first for equalities only. And we introduced already a proxy which could be similar to the tangent cone, and we will show that under some circumstances it is actually the same. And this proxy, which is not the tangent cone but it's something different, is actually f of x, which we call the linearized feasible cone, which was given by all directions p, which are still in this space Rn in which we are moving, but it's the set of all directions which are orthogonal to the gradient of, at this point x, of all your constraints. So that means the product of p with the Jacobian of your constraints is 0. That means in a linearized form your constraints will remain 0 if they are already 0, because that's the first term in the Taylor series. And what we will now prove is the following theorem. We want to make a relation between these two, which allows us then to go on and have something much more powerful than this theorem. And we want to basically translate that by replacing this by the linearized feasible cone. So these are the objects from last time, and already the properties, and now we start with the new stuff. So what I want to prove is actually that under some condition these two sets are the same, and the technical condition that I want to make is called something I will define. And it's actually stating that the rows of the Jacobian are linearly independent from each other. So I make a definition which says, which is called linear independence constraint qualification. And abbreviated, that is called LICQ. And it just says at some point x, which is in omega, LICQ holds if and only if, that's a definition, for the gradients nabla G1 at x, nabla G2 of x, and nabla Gm of x, so that means all the individual gradient vectors are linearly independent. What linearly independent means is clear. So if you want to find a linear combination of all these things which is zero, then all the coefficients must be zero. Another way to say this is actually that the I will just use another formulation for this. It means actually that the rank of the matrix nabla G of x, which we define to be the Jacobian transposed, it doesn't matter, the rank is independent, I could also add the transpose here, but that this rank is M. And you see already something that we should have guessed from the beginning, but I implicitly make, of course, the assumption that M must be smaller or equal than N, otherwise this condition is impossible to satisfy. So if you have more constraints than you have variables, then you are already in a bad shape, usually. Yeah? So then this thing cannot hold. So this linear independence constraint qualification, LICQ, is an extremely important concept in optimization, and it will pop up everywhere again and again in algorithms, and we will discuss it in some detail today. But before I give examples, I want to actually write down the theorem and prove it. So the theorem is actually the following. It's making a relation between these two objects. And the theorem consists of two parts, so x element in omega, that's the condition we start with, and then it just says first that the tangent cone is a subset of the linearized feasible cone. That's something that is independent of LICQ. But the second condition says if LICQ holds, then the two sets are equal. So then we are in a nice situation, because then we have an easy way to write down what this tangent cone is. Maybe before I start to prove that, I want to give one little example so that you get the feeling that these two things are not usually the same, and that they can sometimes not be the same. So I just want to give one nasty example where these two sets are not equal. Yeah? And this example is something, let me just invent something. I just say I have two variables, x is element in R2, and my function g is consisting of two functions actually. So g of x is consisting of a g1 of x and a g2 of x, these two constraint functions. And g1 is given by, I will illustrate it at the same time, makes it easier. Here we have x1, here we have x2. And I want to actually have one constraint that describes this set, and the other constraint will describe this set. And I will do that by just saying that I have here actually x1 to the power of 3 minus x2. That's one constraint, and the other constraint is x1 norm to the power of 3 minus x2. Two constraints, both are differentiable everywhere, twice differentiable even, and they describe actually one. This is a set where g1 of x is equal to 0. Yeah, so you see that the x2 is actually x1 to the power of 3. So it's describing this curve. The second set is saying that the x2 is actually the modulus of this, and on the positive side they will be the same if x1 is positive, but on the negative side they are not the same. So what will be the feasible set? What is omega for this example? Let's think of what is omega. That's easy. It's the intersection of both sets where both constraints are satisfied. So it's actually this part until here. 0 is included because it satisfies both constraints. So if you're at 0, this point is still part of that whole thing. From here on, these two sets divide, and it gets a bit nasty. And on most of the points here, the tangent cone is a simple object. It's just the tangent, the thing that we think is a tangent. So there is nothing to define and to discuss. But at this point, which is a feasible point, we have a problem, namely we cannot move in this direction. There's no feasible curve in that direction. So what we see immediately is that the tangent cone at this point, so the tangent cone of omega at the point 0 is just the set of all p where actually the first component p1 is positive and p2 is 0. So it must be in this direction exactly. These are the only directions, the only feasible curve that we can move in is this direction. You agree with that? Okay, now what is the linearized feasible cone? So f at the point 0 will be this set of all p's that satisfy these constraints in a linearized form. So let me compute, actually I can write it in this form. It's g1 gradient transpose p equals 0 and g2 gradient times p should be 0. And of course this x is 0, so sorry for that, it's 0. So it's the gradient, the first gradient times p should be 0, and the second gradient, that's the same as writing it in, where did I write it? There's the definition, right? So it's actually every component of the vector that I have here in the definition of the feasible set, the linearized feasible set. So all these things should be 0, so let's compute these gradients. So what will be nabla g1 at x? Of this first gradient, it will depend on x1, actually 3 times x1 to the power of 2, and here it will be minus 1. And the other will be a bit different. Actually, it will have a sign change. So it will have the same component here, minus 1, and here it will be 3 times x1 squared. But then multiplied, depending on, for the positive values it will be the same, but for the negative values it will switch the sign, so I can just add signum of x1. But because it's 0 at 0, it doesn't matter at 0. Yeah? So the derivative at 0 is anyway 0. So what you know is that these two vectors at 0 are 0 and minus 1. So I can define this thing as p, and then I have here 0 and minus 1 transpose p, and the other, that should be 0, and 0 minus 1 transpose p should be also 0. Is everything okay, or anything not? No, okay. So I have 2 times actually the same thing, and this same thing just says that, what does it say? It says actually that p2 should be 0. p2 should be 0, and here p2 should also be 0. So it basically says it's this set of all p, so that p2 is equal to 0. And that's at p1, so the direction in this direction can be completely free. So you see that there's a difference. What we see is that the real tangent cone for this example is indeed part of the linearized feasible cone, as the first statement of our theorem will say. What we also see is, and so it's completely compatible with the theorem that we will prove, that we do not have LICQ because this vector and this vector are not linearly independent. Yeah? So these two constraint vectors are not linearly independent. Okay, so this is a little bit of motivation. So why this is not always the same? You might say they look so similar, and probably they are. In most cases they are the same, but only if this LICQ condition holds. They turn out to be, in this case, because we have 2 times the same constraint, even here LICQ does not hold. Yeah. On this, if you would pick any other point, you would have 2 times the same gradient, so they cannot be linearly independent. Still, there the tangent cone is also the full direction, and it will be equivalent to the linearized feasible cone. So there are some cases where actually LICQ does not hold, but these 2 things are still the same. So that can happen. That's not excluded by this theorem. It's only in this direction. Okay, but this theorem we need to prove, and we don't want to just accept it, so let's just try to prove it. So I want to prove the first part first, so this little statement. What does it mean what do we need to prove? We need to prove that a vector which is in the tangent cone will be also in the linearized feasible cone. That's all that we need to prove. So what we want to show is that P element in the tangent cone, that this implies that P is element in the linearized feasible cone, at a feasible point X. That's what we want to show. And how do we show it? We assume this and then we show that. So what do we assume? P is in the tangent cone. What does it mean? It will mean that there exists a curve x bar of t, this curve that we said, so that x bar of 0 is equal to x. X was this point at which we look at. Maybe I give it a star, so then we can distinguish it from other x's a bit easier. So we say that x star is element in omega, so it's a feasible point, and then we just have a different notation. So we have this curve, and this curve actually has the derivative dx bar by dt. At the point 0, it will be in the direction p. And of course, this curve is completely contained in omega. And because this curve is completely contained in omega, it means actually that this fact means that g of x bar of t will always be 0. It must be always 0, because otherwise the curve would not be in the feasible set. But this will also imply that the total derivative of this whole thing, g of x bar of t, will be 0, because something that is 0 will remain 0. And this is where we get actually to the point. So what is the total derivative? We have the outer derivative and then the inner derivative, and that is actually just equivalent to saying that nabla g of x bar of t transpose, that's actually the outer derivative, times the inner derivative. The inner derivative was dx bar dt at t is equal to 0. So that's what we conclude from that. And now we apply this whole thing at t equals 0, and then we see that nabla g at x star transpose times p, because that was the derivative, is 0, and that means p is element in the linearized feasible cone of fx star. So that was pretty easy and nice and clean. So we see what we got as an intuition here from the example can easily be confirmed, and they are really related, these two sets, the linearized feasible cone and the tangent cone. But now we want to prove the second part of the theorem, namely that if LICQ holds, that then these two are the same. And here we need to construct a curve in order to actually, what we want to show is that if we have a P in the linearized feasible cone, that this implies that P is element in the tangent cone. So it's a bit more complicated because we have to construct this curve, but, and that's the good thing, we can assume LICQ. So this is the two things that we can assume. Yeah? So we have LICQ at this point, and so. And before we go on, I want to do a quick look at the matrix. This matrix which needs to be of rank m. And I want to look at this. What does LICQ mean actually? So LICQ means what I said, is that this Jacobian matrix, this thing has full rank, and that means actually this matrix consists of all the gradients of the example of the component functions, and each gradient forms one of the rows of this function, and all these rows are linearly independent. And so LICQ was actually that this has rank m. Yeah? So that's what we said before. But it means basically that this matrix here, maybe I give it the name also JG at x star, so Jacobian. This matrix will look like a flat matrix, so it's actually m rows and n columns. So that's how this matrix looks like. And what we can do with this matrix, and which I want to do with this matrix, I want to use for a moment the singular value decomposition, which you know exists for every matrix. And because a singular value decomposition is a useful tool, it might help us to understand more what actually LICQ means, and also in the geometry of our feasible set. So I will do an SVD, singular value decomposition, of JG at the x star point. Yeah? So that's what I will do, and maybe, yeah, so I have now already two notations for the G. Maybe I just abbreviate it to just call it G, J, okay? Then we have a bit less to write. So this is always the same matrix, and I need to look at this matrix quite a lot. So how will be an SVD? How does it look like? You remember J was given by something which was a product of three matrices, where we had U, S, and V transpose. And these matrices would be so that the middle matrix has the same shape as the matrix that we end with, the main matrix, and it had only positive diagonal or non-negative diagonal entries. And then it had a small square orthogonal block here, so U, and it had a big, in this case it's the reverse, this was the V transpose. Yeah, so this is the S, all together is the S, and this is the U. And what you see already is because here are all zeros, yeah, so here is actually N, and here is N, this is M, and this is N minus M. The remaining columns are zeros. And because it will be convenient for me, I will decompose this V directly into two parts, namely one which is multiplied with this block, so which corresponds to the first M, and then the other which corresponds to the last NM rows. And I will call them directly Y transpose and Z transpose. It's just renaming. So I basically say that the matrix V is consisting of a Y and a Z. And then if I transpose it, I'm back at this. And what we know is that this and the U, they are orthonormal matrices. Okay? So we just look at this matrix. This singular value decomposition always exists. So in that sense, we didn't really do anything new and exciting. But we can now get a grip on what does it mean actually that all these vectors are linearly independent, or that the rank of this matrix is M. It's of course meaning that all the entries on this diagonal, all the singular values are positive, strictly positive. There's not a zero, but they are all positive. So this matrix here is actually invertible. So we have LICQ means actually now it's equivalent to saying that the singular values sigma 1 up to sigma m are all positive. Yeah, and there are exactly m values on this diagonal, of course. Are you all on board? So the singular value decomposition was just a bit overkill. We can get many more things than necessary from it, but I think it's useful to think of the singular value decomposition at the boundary of this, because we will need it also later. So I wanted to introduce it already now. What is now interesting is that we can, based on this singular value decomposition, we can have a very easy specification of what is this linearized feasible cone. So what is actually f of x star, which was actually the set of all p that have the property that this Jacobian, I will now abbreviate it like this, j times p is equal to 0. So which values will have this property? It will be all the values p that when you multiply them with this whole thing, they will get 0. And because this is an orthonormal basis, so every the y's, all the rows that we have here in this y transpose and the rows that we have here in the z transpose, they are mutually orthogonal. So whenever you multiply some of the rows of the z with this matrix, it will in the first part give only zeros. And this is the first part is what will survive due to this part. So anything that is actually a linear combination of the columns of z, will be 0. And on the other hand, everything which is not in the columns of z, which will be on the other part of the space, it will be y. And so that will survive because these are all positive. So whenever you have something, so you could actually say p is equal to y, and I call this maybe, maybe I call it u, little u, right, plus z, and this is a little v. Then I know directly that u must be identical to 0, and I can directly say that this is actually the set of all p, so that there exists a v with p equals z times v. And v is of course in the appropriate space. I could say v should be element in R. The basis that we have here is actually n minus m. So these are the remaining degrees of freedom, and that's actually a parameterization of our null space. I could also, so this was a bracket for the proof, could also say that this whole thing, so the linearized feasible cone, x star, is nothing else than the null space of J. That's another way to say the same thing. But the good thing about the singular value decomposition, Z is a basis of null space. So that is a beautiful way. We have now an orthogonal basis of the null space. So if you think of this in the example, okay, this example was not the best one, but think of the example that we had at the beginning, where we had just one constraint, and at any point we could compute this linearized feasible cone. We have an orthogonal basis of this null space. That means basically a unit vector in the right direction, and we know that all feasible vectors, all vectors which are in the linearized feasible cone, they can be composed by this, they can be written in this form. Yeah? Okay. So now there's one little thing that I want you to notice. It's completely trivial, but I think it's a little lemma, so to say. And it says that if P is in the linearized feasible cone, then it means actually that P is equal to Z times Z transpose times P. So if we project P into the tangent space, and then we augment it again, then it is it's just coming out unperturbed. And the reason for this is that that itself was given by Z times V, and then if you take it, there is a unit matrix, and then it's Z times V again. So the proof is P equals Z times V, and then P Z transpose times Z times P is equal to Z transpose Z V which is equal, because this is also normal, z times v, which is equal to p. Okay, so it has this interesting property. If you are in that space, you can actually project into the tangent space, and you will remain in that tangent space, which is another way of saying P is in this tangent space. Okay, what we want to do is actually we want to construct a curve, and this curve, so I just say the aim, what we need to do is we assume all these things. We know already how we can characterize P, and P will be somehow of this form, it will have this property. We have the LICQ, that means that we can look at these null space bases and also this y here. But what we want to construct is a curve. And this curve will be a nonlinear curve, so we cannot use linear algebra anymore. And what we can do is we can use implicit function theorem. And what we want to construct is a curve which has two properties. Namely, first, it should have the property that it's remaining in the feasible set. So it should have this property. It should, of course, start at x star. And it should actually have the derivative of at p. And so what we want to have, we want to construct x bar of t with dx bar dt at 0 equals to p. That's what we want. And what I propose here is actually to construct this curve using an implicit function representation. So what I will actually define is a function f, which depends on x and on t. And it is a function, maybe I should say, yeah, I will first define it and then we say what we want to do. So this function should be, the first component should just be that it's constraining x to be a feasible point. Yeah. The second thing is that I want that if I project my curve onto the tangent plane, then I want it to be equal with t. So here I have minus x star, maybe I make brackets, plus t p. So this is what I want. Sorry, this x equals 0 is not what I want. So I require this function to be 0. And now let me first count if the residuals make sense. So here I have n conditions. Here I have n minus m conditions, because the z is actually n minus m columns, which become rows here because I transpose it. So f is actually a function which maps from Rn and R, so for the t, into Rn. So that's already good from the dimension perspective. And in order to be able to apply the implicit function theorem says if this function has a non-singular Jacobian at the point, at which point I will specify it at a moment. So I want to actually look at this point, f of x star and 0. So this is the point where this function is definitely 0, because if I put here a 0 and here an x star, then this thing is 0. And if I put x star here, it was a feasible point, so it will definitely be 0. So that's also something nice, so we can use it. What I also want to look at is the Jacobian of this function. So df by dx at any point, I can first compute it maybe. But why don't I compute it directly at the point where I'm interested in? Then we save some writing. So I evaluate it exactly at this point. And what will be this this derivative? It will be the Jacobian of j with respect to x. So it will be j of g with respect to x. That was exactly our matrix g. And in the second part, this is now differentiated with respect to x. This is fixed. T and p are also not x. So this will be actually z transpose. You agree? And now I claim that this is invertible. And why? Because we can use now our singular value decomposition, if you like. And one way to look at this singular value decomposition, I should say, and I didn't say it here, is that you could just say So J can be also written as U, and then this diagonal block here, and then Y transpose. And I left out all the zeros because they are zero anyway. So they will not contribute to anything. So there are zeros multiplied with these things, they will not change the matrix. You agree? Okay, so I can actually write this J in this form, so I have actually, maybe I'll call this S plus or something, because it's a positive values here. And now we have here a U S plus Y transpose and Z transpose. And of course I could also write it in this form. I could have U S plus 0, a unit matrix, 0, and then here, times Y transpose and Z transpose, just to make it more visible. So this is of course the same. I mean, it's just a decomposition of the two matrices. This is orthonormal, so it's clearly invertible. This has an orthonormal plus a positive invertible matrix, so that's invertible. That is a unit matrix, it's invertible. So this is surely an invertible matrix. So we can actually assume we have the conditions for the implicit function theorem. And now we can use the implicit function theorem. That was all that we need to get a curve x bar of t, which solves this equation. It has the property with this function f of x bar of t, comma t will be 0 on this curve. And the curve will of course start at the point where we are. So the only thing that remains to be proven is that this curve actually goes into the direction of p. And in order to show that, so what is dx bar by dt at 0? This is also where the implicit function theorem helps. I don't know if you want me, maybe I do this intermediate calculation so that you can always use to remember how this derivative formula that I will now state comes. So I will derive it, so to say. If you know that this is 0, then you know also that df by dx times dx bar by dt plus df by dt will be 0, because that's the total derivative of that whole thing. And if it's 0, then also the derivative will be 0. I can invert this because that matrix is invertible, so then I get exactly a minus sign on one side, because then this thing is isolated, and I get df dx at 0, at x star 0 with a minus 1 times df by dt, right, at x star and 0. That's what we get. That's the usual derivative from the implicit function theorem. And now we go through our computations. We know already this matrix here. Maybe I do it here. So I have a minus sign. I have then, there are many different ways to write it, but actually I think I prefer this thing. I will just write it like this. I know it's invertible, so I will not do many more. No. I need to decompose it. So let us invert this matrix. And how do we invert it? We invert it step by step. So one is actually to have here the y and the z. That's the first part of the inverse. So this thing is the inverse of that. And now the second part of the inverse is this thing. So we will have here an s plus to the minus 1, a u transpose, a 0, 0, and a unit matrix. So you agree that this is the inverse of this matrix. And now we need to compute this partial derivative. And this partial derivative is relatively easy because there's only one t here. It comes with a minus and a p and a z transpose. So it will be actually, the first component doesn't depend on t. It's actually a vector now. And the only component that depends on t is this thing. It's z transpose p with a minus sign. You agree? And now we are nearly done, because this is now very easily seen to be, we have the Z transpose here with the minus sign twice. This thing will actually be multiplied only with a unit matrix, so it doesn't change anything. So here we have this division, so that goes in here, and then the Z transpose and the Z and the Y. So what we will get here is that this part will be only multiplied with that part of the matrix. The 0 here will be multiplied with that. So we get a 0 at the front, at the top, and at the bottom we get Z times Z transpose times P, which by our little lemma was equal to 0 and P. This is somehow wrong, right? Somewhere I made an error. You can help me to find it, because the dimensions don't match. So this must be, of course, yeah, exactly. So I have this 0, which is staying a 0 and then multiplied with this y, but there is no division of this vector. So this 0 is just not there. It's just not contributing to the sum, because these two things are added together. So this is wrong. So it's just this thing. So there's only a p. But that's it, exactly. So that's equal to p, and that is what we wanted to show, right? So now we have constructed a curve, and its derivative at the origin is actually our tangent vector. So we have proven it, and maybe we should look, where did we need LICQ? We needed it in order to be able to compute this decomposition into null space and range space, so to say, of our Jacobian. And that was an important ingredient here. Okay, so now we have proven a little theorem which allows us to state one condition which I want to end this first hour with, which is a restatement of our theorem that we had. That was variant 0, we said. Yeah. Now let me state the second variant of our optimality conditions. So it's actually saying, let's assume that at x star is a local minimizer, and LICQ holds at x star. So this is of course an extra assumption, we didn't make it before, but if we make these two things, then, okay, x star is feasible. This is, I always state it again because I don't want to forget it. So that's a logical thing that needs to be satisfied. But also that all p, for all p that are element in this linearized feasible cone at x star, we have that the nabla f, the objective function at x star, p must be bigger than 0. So that's actually just a rephrasement of what we did before, just that we replaced this tangent cone with a linearized feasible cone, because we can now do it because we have LICQ. So until now, nothing really big changed. What we will do after the break is actually look at this geometry a bit more. There actually the statement that one of you made the last hour really holds, because this linearized feasible cone by definition is the null space. So this is actually a space, it's not a cone, it's a tangent space, this thing, for equality constraints at least. So this will actually just mean that we should be 0, because we can always have the positive and the negative p inside the set. So this will imply that in all directions in this space we should be 0, and then this will, maybe I should already say that this last condition, maybe I say it here, A, B, and B is equivalent to just saying that for all P in this linearized, I stated step by step, f of x star, we have that nabla f of x star transpose times p is equal to 0, because we can always take the positive and the negative. So if there is any non-zero positive component, then we could just take the negative p, and then we would have already a descent direction, and so that cannot be. But it also means that for all v element in Rn minus m, so if you take an arbitrary v from n minus m, it must hold that nabla f transpose at x star transpose times z times v must be 0. Clear? Do you agree? Because all the components P which are in this null space or in this linearized feasible cone, they must have the property that they are actually, that you can obtain them by v times z times v, where z is this basis of the null space. Yeah? And if that should hold for all v, then it's also equivalent to just saying that nabla f of x star transpose z. Okay, this one is now a lying vector, but it's actually 0. Because if it's multiplied with anything, and it always must be 0, then it must be 0 itself. So we have somehow, you could also transpose this thing just for clarity. So we have a gradient of f of x star, which is orthogonal to the null space of our constraints. That's not so surprising. You remember our picture. This was the optimality problem that we gave as a motivating example. It was at this point that we had the tangent space in this direction and the gradient in this direction, and that was the only point where we had optimality. So we have actually this orthogonality relation is expressed here. And what we want to do after the break is we want to use simple tricks in order to derive even more constructive optimality condition, which extends this variant of this theorem, which we have already in this form. And what we will do is we will introduce now, finally, the Lagrange multipliers that we had already once at the theory part, but we will introduce them in a very different way. Let's do that after the break. We start 15 past. I suggest we continue. We are still in the process of proving optimality conditions for constrained problems with equalities. Still chapter 11. And what we just proved is that, I repeat what we wrote on the blackboard, is a first variant of our optimality conditions. So x star local minimizer and LICQ. That implies, of course, that x star is feasible. I repeat it and repeat it, but also that nabla f, the gradient of our objective function, if we multiply it with the z basis vectors of our null space, then this must be 0. So that's what we just proved. And what we will now need to use, and which we already introduced, is the Jacobian. You remember the nabla g of x star transpose was just called j, and we could decompose that as u times sigma, actually plus, I take this plus part only, and then we had here the y transpose. And we know that y is actually orthogonal to the z, because it was this other part of the basis. So that's what we know about this Jacobian. And now I want to just make a different statement about this last condition, which is funny. You will see. So what I will say is actually, I will observe one thing. And I observe that nabla f of x star will be, of course, like every vector, you can write it as something which I could call, it has a y component and a z component. And maybe I call this, I called it u and v before, right? So I could just call it u and v now. But this is always possible. And what we just stated here is that if you take the product with any of the z's, then it should be 0. If you multiply this whole thing now with a Z transpose, so then this thing will be 0 anyway, and this thing will be a unit matrix. So it already, we know already that this V part must be 0. So we know that actually the Y must be in the Y, the nabla F must be in the Y space. That's actually this condition, B. So B is equivalent to nabla F of X star, that there exists a U so that this holds. So now I can also use the fact that I can invert this U, this big U and this S plus. They can both be inverted if I have LICQ. And that means that I could also say it's equivalent to saying there exists some, maybe I call it U tilde, yeah, because it's a different U, so that nabla F of X star must be equal to Y S plus minus 1 U transpose times U tilde. Oh, this is actually not what I wanted. It's without this inverse. It's just because this is an invertible matrix, I can just use it this way. So actually this statement is equivalent with this statement. And now I look again, and what is this thing? This was actually the concatenation of nabla G1 at X star up to nabla, transpose nabla Gm at X star transpose. And what I have here is actually the transpose of that matrix, right? So this is actually as the same as nabla G of X star times U tilde. So it's just some rescaled component in this space of the Y's. And what is now interesting is I will just basically call the U tilde, I will call it lambda. That's just a renaming. Yeah? And it will be something which lives in the space of the Y. But how many components did I have? It's actually element in Rm, because I had M components in this Y space. Yeah? The columns of Y are M columns. And so actually I have already, based on this simple fact, so that if this holds, then the nabla F must be in the space of the Y components, and then I can actually find such a lambda, or I called it U tilde first, but now I call it lambda, so that it is given as the linear combination of the gradients of my constraints. So I can actually say directly X star is a local minimizer, and LICQ holds at that point, implies that X star is feasible, so that's clear, but also it implies A, and B, it will imply that there exists a lambda in Rm, so that the gradient of F at X star is given by the gradient of G at X star times lambda. And because this relation here was so basic, I mean, every vector can be decomposed into a Y and a Z component, and if there is a no Z component, then this holds. And if this holds, then there cannot be a Z component. So these two things are completely equivalent. So these and that theorem are absolutely equivalent. So they are equivalent. And that is now the variant 2 of our optimality conditions. And it is already containing one quantity, which we call Lagrange multipliers, which we just got out of nothing. By this decomposition of our gradient into the two possible components, into a null space component and the orthogonal component to it. It actually turns out that, maybe I first write this a bit more elegantly. You remember we defined at some point the Lagrange function. This is actually all due to Lagrange, so he was the one who came up with this trick about 300 years ago. So we call this function L for Lagrange. It's the function which depends on L von x and lambda, which is just the objective function minus lambda transpose g of x. We introduced that at this theoretical part at the beginning. And there's another thing that is also called with an L, actually a lambda. These are the Lagrange multipliers. Yeah? So Lagrange is everywhere here. Yeah? But what we can use this Lagrange function for is it will actually now just allow us to write this whole thing a bit quicker. So it's all the same, but here we would just write there exists a lambda, so that the gradient of the Lagrange function with respect to x at x star and lambda is equal to 0. And actually we tend to call this lambda star because it's a special lambda, a lambda which satisfies this condition. And if I differentiate that function, I immediately see that I just do it for the sake of completeness. This gradient of this Lagrangian function with respect to x is the gradient of fx, and then it's here you could write it as a sum. Maybe let me write it as a sum for a moment. So it's lambda I and then multiplied with all the gi, but for each of them is taken the gradient of and then 1 to m. And that is of course the same as nabla f minus nabla g of x times lambda. Yeah, so you see now maybe why optimizing people very often have this convention that I use, that you use actually the nabla g as being the transpose Jacobian. At least you don't need a Jacobian transpose anymore in the optimality conditions, and they are very often written by optimizers. So this is already the main theorem. These are the Lagrange optimality conditions. So that is a theorem due to Lagrange, and it's stating first order optimality conditions, and the only assumption that we had to make was that we have LICQ. That was the only thing that we needed as a technical condition, and the reason had nothing to do with the Lagrange multipliers, but it had only to do in order to make that sure that the tangent cone and the linearized feasible cone are the same. And if they are the same, then everything else would be easy and nice. So in order to make this theorem a bit more, or to illustrate it a bit more, or to just give a bit more meaning to it, I want to point out one thing that is the basic fact that we used here, is that there's a null space of a matrix J, and this null space turns out to be orthogonal to the range space of J transpose. That's actually what we used here. It's orthogonal to the range space of J transpose. Yeah, that's actually what is at the basis of this whole thing, and it's all due to the fact that the range space of a J transpose is actually this Y. And the null space, so this is actually Z, and that's orthogonal to Y. So the span, I should say, this is the span of Z, of all the columns of Z, is orthogonal to the span of Y. That's actually what we use, but it's a basic fact that holds for all matrices. And that is the fact that allowed us to decompose, to state that, first of all, what we said is actually this nabla f is orthogonal to every vector from the null space. And that is equivalent to saying that the nabla f can be decomposed as a linear combination of the vectors of the range space of the transpose. Okay? So this is only like a little thing at the background, but what we remain and what we keep is that these two, and maybe I write it directly again. So here we have x star element in omega, but what does it mean? Actually, it means that g of x star is equal to 0, and this all was implied by being a local minimizer and LICQ. So when we have an optimum, then we know that it must be feasible, and we know that there must exist lambda star so that the gradient of the Lagrangian is 0. So we derived something that is computational, and in order to show that it's computational, I want to go through a little example. So this is useful. And why is it useful? Because you can now use it to find x star and lambda star together by a root finding problem. You remember the root finding problems are the nice things we can use Newton's method for. But let's just look at an example. Can find optimization candidates, right? So it's not necessarily the optimal solution, but it's candidate points for optimal solutions. And so let me just look at the example which we had, where we had the optimization where f of x was just x2, and it was there was a constraint function g of x which was given by x1 squared plus x2 squared minus 1. So it was this two-dimensional example that we had before, this thing, which we had x1, x2, the lines here. And of course we remember this point was an optimal point, but let's just not assume that we know that, but let's just write down what would be the optimality conditions. So maybe I first do a definition before I do it afterwards. I first do the example. So I just set up the equations that I would need to satisfy, and these would be the I first compute the Lagrange gradient, because I need the Lagrange gradient, right? So I will compute first what will be the what will be the Lagrangian function. It's depending on x1, x2 and lambda, and it will be actually x2 minus lambda 1, but I give it just lambda because there's only 1, times x1 square plus x2 square minus 1. So now I can compute the gradient of this whole thing with respect to x, and it will be 0 and 1, because this I differentiate with respect to 1 and to the first and the second component. And here I need to actually take minus lambda, and then times the gradient of this thing, but the gradient of this is 2x1 and 2x2. So we have this gradient, and now the necessary optimality conditions, first order, this theorem that we had, first order necessary conditions, FONC, for optimality. What do they state? They say actually that g of x should be 0, and that this Lagrange gradient should be 0. And what are they? Actually, I could write them together. So they are actually x1 square plus x2 square minus 1 should be equal to 0. Then it says that this thing should be 0. So that's actually, I write it down. The first component of this whole thing says actually minus lambda times 2x1 should be equal to 0. And then it says that the second component, which is 1 minus lambda times 2 times x2 should be 0. And this is now my set of nonlinear equations which are necessary for optimality. So I have them all together, and they are conditions. They are 3 conditions on 3 variables. So that's what makes it so useful. And I could now look at these equations and say, let's maybe assume that the lambda is not 0. For a moment, then we could say, okay, then the x1 must be 0. If the x1 is 0, then this whole thing here is 0. Then the x2 must be 1. Okay. If the x2 is 1, then the lambda must be 1/2. So I could say that lambda equals 1/2, x1 equals 0, and x2 equals 1 is a solution. And of course, the Newton method can find such a solution. I could find another solution. I think there would be another solution here at the top. This is actually the solution at the top, I'm sorry. Yeah. So this is actually a maximizer for this problem. But I could also find another solution, and that one, I mean, this is of course a nonlinear root finding problem, so a priori I cannot see how many solutions it will have, but it will also have another solution, namely the one that is here at the bottom. I could also use x2 being -1. It will not change the argument here, but if it's -1, then the lambda will be also -1/2, right? Lambda equals -1/2. And yeah, and then the x1 would still be 0. So these would be two solutions I can immediately see, and I don't think there are others, but of course you can prove maybe, or you can prove me wrong if you want. The point is, the usefulness of these conditions is that there are exactly as many conditions as you have unknowns. Yeah? So there's another thing which I want to share with you because it's interesting. I want to point out that g of x is actually nothing else than the negative gradient of the Lagrangian with respect to lambda. So that's a bit funny. Why? Because the Lagrangian was just having the lambda here, and if you differentiate with respect to lambda, then the g is coming out, right? So actually the necessary optimality conditions, j x star equals 0 and nabla x lambda of x star and lambda star equals 0. So these conditions you could also write down as just saying that the gradient of lambda with respect to lambda, of L with respect to lambda should be 0, and the gradient of L with respect to x should be 0. And if you want, you could also just combine it all and just say, just to have a shorthand, so the gradient of, with respect to all of its variables of the Lagrange function at the optimal solution must be 0. So you see it's a very powerful function. This Lagrange function itself contains everything. If you have the Lagrange function, you can formulate from its first derivative necessary optimality conditions. How many is it? It's actually n plus m conditions and n plus m unknowns. Yeah, because you can count how many conditions do we have here? M conditions here, and here we have n conditions because the gradient is with respect to n, and the unknowns are n and m, dimensional. So the dimensions match. Okay, so we have a rough understanding, and now we call actually a point. Yeah. If x star satisfies these first order necessary conditions for optimality, which I stated in the theorem and repeated several times, we call it a stationary pointer. So a stationary point is a point where this condition is satisfied. It doesn't mean that it's an optimal point, but it's just to have a name for it. Yeah, we want actually to continue, and I want to relatively quickly, and this is possible now because we did all the hard work already, I want to go to second order necessary and second order sufficient conditions for optimality. And yeah, let me do it. Briefly. I think we can make this even a new subsection. So it's 11.2. It's about second order conditions. And what we want now to do is we want to look at the second derivatives of the Lagrangian and how they tell us something about the optimality or not. And the interesting thing is that everything gets relatively quickly, and I will state with two theorems first, and then we will prove them. So the first one is second order necessary conditions. And this says if we have an x star, which is a local minimum, and LICQ holds at this point, and of course we have sufficiently highly differentiable functions f and g, then there exists a lambda star so that, I could just, so that the gradient, so that g of x, maybe I directly write it in this very short form. X and lambda of x star and lambda star is equal to 0. So that's like the shortest form possible, just to save writing. So that's actually then first order necessary conditions are satisfied. That's a bit trivial, right? So that is nothing new. We proved that already, but I just repeat it because I want to use it for another statement soon. But the second thing is a bit more interesting, and this says actually that the matrix that I get, and we will prove that in a minute, when I take the second derivative of my Lagrangian with respect to x, at the point x star and lambda star times z, that this whole matrix must be a positive semi-definite matrix. And Z is still the null space basis from before, so Z will always be the null space basis here. I want to actually state, so this resembles very much what we had already before. So this is like stationarity, okay, now it's a Lagrangian. This is like positive definiteness of the Hessian, you remember that, but now it's actually in the null space in the directions in which we are allowed to move. So it's a projected Hessian. So this thing is the reduced or the projected Hessian. And please note that it's the Hessian of the Lagrangian. And maybe I want to directly state the next theorem, which is, so to say, accompany it, and it's the second order sufficient conditions. And this is the other way around. And here we actually have the first time that we have sufficient conditions, and what we will expect is that we will have a strict inequality here, and that if this satisfies and this is satisfied, that then we will have a local minimizer, and that's exactly what I want to state. So if LICQ holds at x star, and if, and now I repeat the two conditions, but slightly different, but yeah, so, and if there exists a lambda star so that it's a stationary point, x lambda, x star, lambda star equals 0. And second, there holds actually this condition that the z transpose, the second derivative of the Lagrangian, at x star and lambda star, z is a strictly positive definite matrix, then x star is a local minimizer, or minimum point. So that's the second version, and of course this is really useful because it allows us for the first time to check if actually some point satisfies the local optimality conditions or not. And now you say, okay, this is interesting. This first thing is trivial, right? So this part we don't have to look at. This thing with the metric z and with the second derivative of our Lagrangian, that's what really matters. And so there I want to go through a proof, and this is not so difficult once we have introduced the Lagrangian. And here the whole power of Lagrangian optimality conditions comes into play. So I will prove these things. And what I will be able to do is we will assume LICQ and stationarity already. Yeah? Because, to make all together, assume LICQ and stationarity. That means we have a pair of x and lambda, so they exist, we have them already, and they satisfy that g of x star is equal to 0 and that the gradient of the Lagrangian at this point is also 0. And now I want to look at what will be the objective function in the neighborhood of this point x star. So how does f of x look in the neighborhood of x star? But it's not the neighborhood alone, it must be the neighborhood in the feasible set, because we should only compare it with feasible points. And so what we will do is actually for x in omega, for any x in omega. So we will have to compare it with all the other feasible points which are in the neighborhood. And what we do here is a very funny trick. We will just say f of x is given by, I add 0, f of x minus lambda transpose g of x. Why can I do that? Actually, I will take lambda star even. I take this optimal value. I can do that because g of x for all feasible x is 0. So it's actually equal to the Lagrangian function of x and lambda star. That's it. Okay, so there's equality for x in the feasible set. But now that I've done this, I can use Taylor. And that's what I will do. So I will actually use Taylor expansion and I will say, okay, it's actually lambda, the Lagrange function at the point x star plus the first order Taylor series. So I take only gradients with respect to x now. X star, lambda star, transpose times x minus x star. And now I can take the second order term. And I will take it, and it will be actually x minus x star transpose, and here will be a 1/2 in front of it, and here will be the second derivative of the Lagrangian at x star and lambda star times x minus x star, and then there will be plus a term which is of third order. So that's the Taylor series expansion. And of course, okay, this is now a bit redundant, but this is of course equal to f of x star again, right? So that's just the same argument but reverted. So this is clear. This thing, I assumed already that it's stationary, so I know this part is 0. So it will be 0. Then it will be plus something which is x minus x. Okay, I will not repeat it actually, I will just say this whole thing. And plus also this thing. So I don't have to write them again. But what I see immediately is that what I got is from before. I have my function value at x star. Then I have nothing. And I have a second order term which depends on the product that my feasible point makes with the difference to my optimal solution multiplied with the Hessian of the Lagrangian plus higher order terms which will be dominated by this. So now the first thing is if this for the second order necessary conditions, you can I mean, this one, as I said, is already proven, so we assume all these things, and then what we want to, this equality always holds. What we just want to show is that we also must have a positive semi-definite matrix here. If we would not have, if there would be a negative eigenvalue in this matrix here, in the direction of the null space of our constraints, then it would actually mean that there is a direction, a curve, that starts at x0 and that goes into the feasible direction, which will create some difference vector here, which is actually having a negative product. So if there would be a negative eigenvector, an eigenvalue in this matrix here, in this protected matrix, then we could actually find some curve so that this point would become negative, and it would, for very short parts of this curve, be dominating that part, and then we would have a contradiction to optimality. So in that sense, this equality already allows us to prove this first theorem. The second thing is, now assume that this holds, so that's all what we assumed here, but that also this thing has only positive eigenvalues. And now, if we take I could actually add the curves here if you want. Maybe I should. No, I don't want to do it. It's elegant enough, I think. So if you see, if this matrix is positive definite on the null space of the directions in which I move, then there is actually a lower bound where this matrix will be strictly bigger than the square of this distance. And for small enough distances, it will also dominate this term, and so then you have already established that it must be actually that x star is the best optimal point in this neighborhood. So that's a bit intuitive, but I think you immediately see the trick was to add this little thing here and to use the fact that the Lagrange gradient is stationary. So these are the two tricks. And then we have a simple, this value at x star plus a quadratic plus something higher order, and this quadratic, of course, needs to be only checked in the directions in which we can move, and these are the directions which are given by z. Yeah? So what I maybe should make as a remark is that x minus x star should be, so to say, replaced by x bar tilde minus x star. Yeah? So that's this feasible curve. Yeah? So, and then I could actually look at d of x bar tilde by dt will be always p, and this p will always be represented at z times v, and then
x minus x star, you mean in this neighborhood, right? That you want to show that x star is the best.
Yes. Now, what I wanted to just explain or give extra motivation, which I did already in words, why we have to project it into this direction z and z transpose. Yeah? And the reason is that up to first order, this difference x minus x star will live actually in the space z times some vector v, because we can only move in these directions. So z spans the directions in which we can move, and only these directions we need to check. So it doesn't matter in the other directions what curvature we have in the Hessian. It's only in the null space direction. So it's this reduced Hessian that matters, and that is the main quantity of interest for the second order conditions. And I wanted to look at both conditions together because it's basically the same idea behind the proof. This was a bit short. Maybe I took some shortcuts here, but I think you see, after maybe assembling the thoughts again, you would all agree with me that this is giving you a complete answer and a proof of these two theorems. Okay, I think we don't have time for an example, but the good thing is we have exercises. So what I would suggest is that for this example that we looked at here, we do the derivation as one of the exercises and check if the second order sufficient conditions are satisfied at the point, to get a bit of exercise with these conditions. Okay. If there are no questions, I don't see any, then I thank you, and we see you back on Friday at 2 o'clock. Thank you.